Hello everyone, my name is Rujuta Mokal. I am a third year student at Rutgers University. My research poster for today focuses on the muon proton scattering experiment, or MUs. This experiment aims to solve the proton radius puzzle, which is a 4% discrepancy in the proton radius when measured through muonic hydrogen spectroscopy as compared to normal hydrogen spectroscopy or electron proton scattering. The MUSE experiment uses a beam of electrons, muons, and pions whose interactions with the target proton are measured using detectors and other electronics. The data that we get from our detectors is further analyzed to get a more accurate value of the proton radius. So in my poster today, I will be focusing on the RF time difference between particles at different momenta. But why exactly is it necessary to study this RF time? So for our cross section, we use Rosenbluth's cross section formula, which you can see right here. And this formula tries to understand the charge distribution from which we can extract the proton radius. However, this formula can be used in its current form only for electron scattering and needs to be modified for muon scattering due to the heavy mass of muons. As a result, it is essential for us to identify which particle is hitting our target. This is where the RF time difference comes in, since it provides the most basic information required for particle identification. But what exactly is this RF time? So, our beam particles are produced when a proton beam hits a carbon plate. Some of these beam particles enter our channel about every 19.75 nanoseconds. The RF signal is generated by an accelerator located at the beginning of our channel. So for our RF time, we consider the time of flight of these particles from the beginning of the channel to the end of the channel at the beam horoscope. And then we take this time of flight and mod it with 19.75 to get the RF time. For my analysis, I try to study RF plot averages, which you can see right here, which are basically these 19.75 nanosecond time windows with particle hits laid on top of each other. Um, for my analysis, I try to take Gaussian fits of these histograms to determine what the time difference between particles would be. And then I also estimate these time difference values from a simple calculation of momentum and energy, which you can see in the method section right here. And I follow these steps with three major goals in my mind. The first goal is to establish the electron stability across our range of momenta. So since electrons are highly relativistic, their velocity doesn't really change with momentum. And we can see that this is true since if you look at the plots in my background section, the electron peak position at negative 154.8 MeV per C is the same as the peak position at 171.85 MeV per C. Sorry. So once I established the electron peak stability, my second goal was to understand the electron muon and electron muon and electron pion time differences at different momenta. So you can look at the plots in my analysis section for this. These plots are RF time on the y-axis and the momentum on the x-axis. In the first column, the blue line represents our calculations or our estimated values, and the data points represent the actual data from our runs. So from this, you can see that the blue line is located slightly lower than the data points. This tells us that the values that we get from our runs are slightly larger or higher than we expect them to be. The actual differences between our estimated values and our runs are shown in the second column at the picosecond level, and we can see that the average difference for pions is about 120 picoseconds, and the average difference for muons is 60 picoseconds. So after understanding these differences, my third goal was to propose offsets in our calculations, which would help minimize these differences between our data and our calculations. And the offsets that I proposed were 0.115% decrease in the momentum and 3 centimeter increase in the path length. while estimating our values. The third column in the analysis section shows these differences with the offsets applied, and you can see that the average difference for pions decreases from 120 picoseconds to 41 picoseconds, and for muons, it decreases from 60 picoseconds to 25 picoseconds. So after analyzing my plots and plotting them, I tried to draw three major conclusions. So the first conclusion was that the muon electron and pion electron time differences that we get from our runs are larger than what we expect them to be. The second conclusion was that the offsets that I applied seem to be doing pretty well, since they they reduce our differences by 66% for pions and 58% for muons. The third conclusion was to understand that the offsets in our calculations are merely a guide to the offsets that we can apply to our actual data once we understand our electronics better than we do currently. We are also looking into several other possible effects at tens of picoseconds level that might help bring our data and our data and our calculations into a better agreement. So that's all I have for my poster today. Before I conclude, I want to thank Professor Gilman for giving me this opportunity, and Win and Shraddha for answering all my questions. And thank you for watching.